So we're getting ready to talk about numerical methods for solving differential equations. This is um, this is where we have a differential equation. Maybe it's something that we can't solve by hand, or something that would be extremely difficult to solve by hand, but we need some kind of approximation at a specific x value or at a specific xy ordered pair value, since our differential equations could be in terms of x and y instead of just one of the two variables. So how could we do that? And there's a couple of different ways. Euler's method is probably one of the older methods. And then we're going to have an improved Euler's method, and then we're going to see something called Runge-Kutta methods. And we're really going to focus on that fourth order, but there is a second order Runge-Kutta method. And I'm going to show you how to use Excel for these. So we're really going to focus on Euler's method in this video. Euler's method is something you saw in Calc 2. So we're just going to kind of revisit that method. We could do these by hand. Doing it by hand gets very tedious. Remember, we're trying to come up with a final answer. That answer, we want it to be a good answer. So um, rounding can definitely be an issue. If you're doing this by hand, and we'll do that in another video, we'll do one or two by hand just for fun so you can see what happens. Then what we're going to want to do is keep as many decimal places as possible until we get to that final answer. So your calculator rounds to 12 or 13 decimal places. Um, for this class, that would be fine. In real life, depending on how many iterations you have to do, that may or may not be good enough. And that's where some of the heavy duty programs come in, like MATLAB, which is backed by Mathematica, um, where you can go in and create programs and write programs in something very similar to C, actually. Um, those types of things will come in handy. So let's get started. If we're looking at Euler's method, here's the format. So it's y sub n plus 1 is equal to y sub n plus h. H is our step size times f of x sub n, y sub n. So this second iteration depends on what you will get from that first iteration. So let's set a spreadsheet up. So I'm going to look at, and I'm going to go back to that page. I'm going to look at this example down here, number 6. I want to solve that differential equation. Notice they're giving us an initial starting point here, y sub 0 is equal to 1, and they're telling us to find y of 0.5, and they're giving us the step size, that h of 0.05. So all of that information is going to go into a spreadsheet. I like to type everything in, that way I know what this spreadsheet refers to and what all my columns mean. So I am going to insert equation. So this differential equation is y prime equals x squared plus y squared. You can use the caret key to get the exponent, and then if you hit space, it will turn it into an exponent. It's one of the nice things about Microsoft's built-in equation editor. So there's our initial condition. We want to know this value, and I'm going to include the step size also. I'm going to move this up to my top one, just so I have that information there. So we're going to need a few columns here. We're going to need a column for X. We're going to need a column for Y. And we're going to need to type in our H value. I'm going to say H equals here, and it's 0.05. I'm going to set the spreadsheet up so that if I need to change this value, then it will automatically change what's going on in here. So it's going to make things kind of nice for us, actually, this way. So that initial point, 0.01, is the first thing that's going to go in under that X and that Y column. So there's 0.01. Now, our X's are going up by that step size of 0.05. So what we can do is type a formula in. We're going to hit equals. We want to base it off that previous line. So do you see how it highlights this in a different color? And then it's got those dots around it. And then we want to go plus, and we want the step size. But we always want this particular block. So I'm going to go up here, and I need to put dollar signs in front of the H and in front of the 1. And what that does is it will tell Excel, I want to keep that cell stationary at all times. So you can see what my formula looks like here. Hit enter. So then it added 0.05 to that previous line. Now if I take this and I drag that formula down, do you see that little square in the bottom right? If I put my mouse over it, it turns into a plus, and I'm just going to copy that down. We want to go down until we get to 0.5. And so it copied all of those values down. Now, our Y value is going to change because we're using Euler's formula. So let me pull up our formulas for those numeric methods again. So Euler's formula says that that next iteration, which in this case would be the iteration for 0.05, would be y sub n plus h times f of x sub n y sub n. So we're going to evaluate our differential equation at that previous 0.01. We're going to multiply it by h, and then we're going to add that previous y value to it. So we have to think about what does that formula mean, and sometimes it helps to think about what that formula means in words. So if you say it out loud and say, well, it means previous y value plus step size times differential equation evaluated at previous point, then I think it will help help what that means kind of sink in a little bit better. So we're typing an equation, so we got to hit equals, and it's the previous y value. So I'm going to click on this block, which is in block B3, previous y value, plus step size. Now our step size is staying constant, so we have to put dollar signs in front of the H and in front of the 1 again. And then times. Now we got to tell it that function evaluated at that previous point. There's not a way just to say reference this cell where I type the formula in, so we're going to have to kind of hard program that in. So our formula is x squared plus y squared. So it's going to be this value squared plus that y value squared. I like putting parentheses around the cell that's being squared. Okay, we also have to have parentheses around the x squared plus the y squared. So don't forget that parentheses set in there. And then hit enter. My formula is missing the 1 there to reference the cell. Hit enter. So we're going to get 1.05. So because we set everything up with formulas, we can drag this formula down, put your mouse over that little block in the bottom right, hold the left button down on the mouse and then just drag it down. So you can see that. So then our final answer, our approximation for when x is 0.5 would be 1.93318. So what's cool about this is we could change that step size. This is a step size for 0.05, but what if we wanted to change it to 0.1? So I want to show you how we can do that. I'm just going to click on this cell. Because we reference the cell in all those formulas, if I type in 0.1 and hit enter, it's going to change all those x values, which will automatically change those y values. So now if we're using a step size, if we're using a step size of 0.1, something a little bit bigger, look at what happens to our values. We're still looking at when x is 0.5, our y value is 1.83. So you can see the difference between those y values. The smaller that step size is, the more accurate our answer is going to be. So just for fun, I'm going to cut this guy out and move it over here. Just for fun, I am going to change this to, let's see, we did 0.1, 0.05, let's do 0.02. So you can see we're not quite where we need to be. We want this to be 0.5. So we can just drag that down. And then we can compare this answer. So then at 0.5, we get 2.00739. So then that step size was a little bit smaller here. Let me correct this. We first used 0.05. So you can see how these values are changing as our step size changes. The smaller the step size, the more accurate this is going to be. We could go 0.01 or 0.001 and just extend these formulas down. Let's do another example of Euler's. And let's look at number 10. So I like to type all this in. We're still using the step size of 0.05. We're going to go to Insert, Symbols, and Equation. I'm going to move this to that top line just so I know what this top line means, what equation I'm dealing with, and so on. we're going to do a step size of 0.05 again. I'm going to pull the Euler's formula sheet back up. So we're doing this differential equation. We're starting here at 0.5, different starting point, same step size. We want to find y of 0.5. And there's the formula we're using for Euler's. So we need a column for x and a column for y. Our initial point was 0.5. That's coming from this information here. Our x's are going to change by 0.5. So to get that formula, it's going to be equals. We're going to go up to cell A3, column A, row 3, and we want to add 0.05 to that. But we want this column to be stationary, so we have to put dollar signs in front of it. If you do not put dollar signs in front of it, it will not keep this cell, so it will end up adding nothing because there's nothing below that. Hit enter. Now we want to copy that formula down. I'm going to make this bigger. So I'm going to highlight the cell. I've got my cursor on the cell. That little block, mouse over it, click on it, and drag down. We want to go to 0.5. So using Euler's formula, it says it's the previous y value. So we're going to say equals previous y value plus step size. Make sure you put dollar signs in front of the step size, row and column, times the function, or the differential equation rather, evaluated at that previous point. So our differential equation is y minus y squared. And don't forget the parentheses there. This is really important because that function, that differential equation, evaluated at that previous point has to be multiplied by the h value, so by our 0.05. So our equation is y minus y squared. So it's y minus that y value squared. And then I'm going to copy that formula down. So then this says that y of 0.5, remember that's the goal, that's what we were trying to find, that's what it says here, is equal to 0.622813. And that's for a step size of 0.05. Now, if we were to move this column, make it wider, if there were more decimal places, then it would expand that. Excel will keep quite a few decimal places. There's some rounding error, but that's going to happen like in the 20th or 30th decimal place, I think is where it stops. It's been a while since I looked at that information, but we're not worried about that. We're good. 20 or 30 decimal places, that's more accurate than what the calculator can do, so we're good. We're good. So once again, if we wanted to, we could change that step size and we would not have to type anything else in here because those formulas are set up to reference this step size. So if we change it to 0.1, you can see how it changes the formula. Now our answer would be 0.623. And that's with a bigger step size. So the smaller that step size is, the more accurate this answer is going to be. So this answer with a 0.05 step size is actually more accurate than this guy. Some of these differential equations um, you'll be able to solve. You can solve by hand and then find what that exact value would be. And some of them you won't be able to solve by hand. So then as far as test quiz final exam goes, what I'm going to ask you to do is use Excel to compute Euler's, improved Euler's, and RK4, the Runge-Kutta fourth method, order method. We'll talk more about that later in the semester.